All right, so welcome everybody. This is hopefully going to be a quick review of generators. So before you start looking at this video, please ensure you understand motors and essentially how we create that spinning armature by using electrical energy and creating mechanical energy. In generators, we do the exact opposite. We basically take mechanical energy in the form of some sort of a moving an object that can now create electrical energy. And the object that needs to move is again your coil of wire, and it needs to move past a magnetic field. So again, this is this whole idea of electromagnetic induction. And it does not matter which one moves, the wire or the magnet. But one of the things I want to point out to you, and this is a really good picture down here, is this is a rudimentary mock-up of essentially how a generator works. So you'll notice that the mechanical and energy is the input. So I physically need to turn my armature, whereas in the motor, the electrical energy causes the armature to spin. Okay, the output is going to be electrical. So the conversion happens within. So again, I still have permanent magnets. So I have a north and a south. And again, please make sure you can visualize that I have magnetic fields that are running through this. Now, one of the things that's really important to be able to see even from this picture is that armature, when it eventually turns, it can either turn so it's up and down, okay? And you're going to see that it's running parallel or it's going in the same direction as those magnetic fields. When this happens, you have very low, if any, electrical output. Okay, so you're not going to get any electricity in this combination. What I need to be able to do is I need to be able to cut those magnetic fields in half. So instead of being parallel, I need to be perpendicular. So again, we've talked about this, that if I can now turn this coil of wire and I can cut at 90 degrees, you are going to get basically maximum electrical output. And the reason this happens is, again, I'm going to be able to take, imagine all of those spinning electrons that are making this magnet magnetic, I can free those up when they run directly at 90 degrees. So this idea of the position of the armature is going to be super important. And again, that gives us our voltage, or basically the amount of push coming out of this. So if I want to essentially make this stronger or make this bigger, there's a few things I can do. Obviously, I can increase the coils of wire, I can turn it faster, or I can use a stronger magnet. So I can do a lot of things to actually maximize the voltage that I'm putting, or I'm creating here. So as you see, we're going to start looking at DC generators. So just for comparison purposes, I just want you to go back to your DC motor. So again, this is a device that's going to use electricity. So this is using it. And with a DC generator, you're creating electricity, or you're converting mechanical energy into electrical energy. So I can usually tell it right away because number one, on this motor, there's a battery here. So obviously it's using it. And I can see that there's a voltmeter here, which is basically measuring the push. So the other feature that I'm going to see is, again, on my motor, I know I have a split ring. So again, that split ring, its whole job was to change the polarity of this electromagnet from north to south, to making sure I always had those common poles as they would push past those permanent magnets. But the job of a split ring here on a generator is a little bit different. It's essentially just to make sure that the brushes are always in contact, and I can always have the electrons flowing in the same direction. This is why it's called direct current. But again, I want to point out, and it's super important you can see this, because you'll notice on this graph that I can actually point out that I have highs and lows. So this at the top is basically the maximum voltage or the maximum push that's generated. I'm going to get that when I have a 90-degree break between the magnetic flux and my wire. So let me see if I can show that to you. So again, obviously I have north to south, north to south. I can draw in my magnetic field lines. So one of the things you'll notice, if I were to take a look here, that when the wire is straight across, you're going to notice that everything is parallel. That is going to be the minimum voltage, or basically zero voltage, because I'm not breaking any of these fields. If I can turn this and I can write this at a 90-degree turn, I now have my wires now sitting at 90 degrees, and they're going to cut through this field. Okay, and when they cut through this field, you are now here. You are at maximum voltage or maximum push. But again, for every time I go through this, you'll notice I have maximum and then I drop back down again. I have maximum, and I drop back down again. So one of the good things is I'm always flowing in one direction. You'll notice I never dip below sort of this line here. I go down to a 0 voltage from whatever this number is up here, and we can change that. But I'm always in one direction, but I always have this dip. So DC generators are very limited in how far they can push this electricity. So when you take a look at the biggest differences between AC and DC generators, this is an important summary. Your DC, we already know this, has a split ring. So again, it's one ring right here that basically has a gap. And that gap, again, allows it to stay in contact. And then when it's not in contact anymore, I can reset. But I'm always moving in one direction. Okay, so one of the things I want to point out here on this graph is I can actually show this is when you're always in this positive range, think of this as moving in one direction. You're always moving, say, to the right, if that helps you. I can now create what's called an alternating current, and I'm going to now slip on different rings. So instead of one ring with no gap, or sorry, with a gap, I now have two rings. So that's the idea of a slip ring, is it's now a two-ring system, and there is no gap. So because there is no gap, I don't lose this pressure. So if I were to draw out, again, another volt sort of diagram, I now, if I am going to drop, but I pick it up because, again, it's going to go to the second ring. So this is basically ring number 1 here, and this would be ring number 2 when it establishes its contact. Ring number 1, ring number 2, ring number 1. So I realize it's dipping below what we would consider a positive to a negative volt, but consider this kind of electricity moving to the right and then moving to the left, moving to the right and moving to the left. I'm always having the same pressure or the same push. And that's the big things. I want to maximize the push or the voltage that's coming out. So when you look at the key summaries of a DC generator, and again, we watched that video in class, please make sure you understand why I would need a DC generator. This was basically would be for small jobs. Okay, so if I'm on a construction site and I need very close or I need a short distance that I have electricity to run over. So this might be, I always have a backup generator if there's a bad storm. That backup generator is going to be a DC generator. It can basically run small appliances for a short period of time, but essentially this would be my generator, and I have then the source or the house that I need to try and support. Okay, so it's over a very, very short distance. Again, the reason being is because of the drop. I always need the electricity running in one direction, but can do that because of the split rings. But it's like pushing a child on a swing. They're always going to come back to you, and they kind of lose their oomph, and you have to keep pushing and keep pushing and keep pushing. If you don't, they're going to stop, and that's exactly what a DC generator is. Other sources of DC generator or DC electricity are things like batteries or, again, a photovoltaic cell, because, again, I always have electricity running in one direction. Its counterpoint is an AC generator or alternating generator. So the big difference here is I don't have the electricity all running in one direction. I'm going to change the direction, and that's because the brushes are always in contact with these commutators. So again, I have one ring here, I have another ring here, and I have separate brushes touching both. Now this again always ensures that there's electricity flowing. But every time I make this full revolution of my armature, by the time I make one revolution, I have to basically switch from ring 1 to ring 2. Because every rotation I have to switch this. So consider this, if you think of this positive voltage and this negative voltage, think of this electrons moving to the right and then moving to the left. I can again keep up a constant push. I can keep up this high voltage over a long period of time. And that's why when you look at why we use AC generators, is this is if I have to transport a high amount of electricity over big distances. And the other thing that's really cool about this, and we're going to learn this a bit different or a bit later, is if I have alternating currents and I have an alternating electric field, I can now actually create another magnetic field. And this is actually super important when we get to this idea of transformers. And there's a reason that when you actually look at the energy that's being transported in the power lines, I can literally step up, say, a 200 volt generator to a 20,000 volts transmission line to get this from, say, the Bearspaw Dam to Arbor Lake. And then I can drop that back down to 240 volts by the time it gets into your house. Because if I put 20,000 volts into your house, I'd blow it up. That's too much push. Think of, again, voltage as the amount of push behind every electron. I can actually give it more or less by using things called transformers, and they have to have alternating current. So again, a really important summary is on this page. Make sure you understand that everything that comes out of your wall is created by alternating current. So these are created by our oil and gas. So when we burn coal, we basically are turning an alternating generator to basically create electricity. And we do that so that we can push it over large distances. But again, once I get it into your home, and I need to now maybe run it on my laptop or I need it on my fridge, all of our devices need direct current. Okay, your light bulb will not work by having the electrons moving left to right. So that's why everything you have is going to have an adapter. Okay, so when you actually look at plugging in your laptop, especially if you have like an Apple device, you'll see those square boxes. That adapter is literally going to take AC and it converts it to DC. And you'll notice that there's a fair amount of heat and resistance when this happens because those electrons are trying to do this, and I'm forcing them into going into one direction, which all of our circuits actually need. So we're going to learn more about this, but essentially this is how your alternating current essentially works. So I have a power plant. Again, this is going to create alternating current. It's going to use, again, those two slip rings. So it's important that you understand that AC has a slip ring. And again, I can now create a big push. So I can create a very large voltage as we move through these power lines. So this is going to be at the end of outcome 2. We're actually going to understand this idea of a transformer and this idea of a step up or a step down. The only way I can do this is if I have alternating current. And then once I get it into my home, my devices can now use DC. So again, make sure you can identify the key differences between motors and generators. Motors basically convert electrical energy to mechanical energy. So again, think of this as they use electrical energy, and the generator basically creates that electrical energy. So that's an important thing. I can actually always tell I have a generator because I'm going to connect a voltmeter or a meter, which is, I think of a thermometer, that can literally tell me the voltage. Now, when I'm converting from one form of energy to the next, of course, it's never 100% efficient. Again, anytime you feel an electronic device, you feel this heat. Heat is a major issue when you look at electrical devices, and especially when you're transforming or transmitting electricity over big distances. We want to try and keep that heat down as much as possible. So a lot of you, as we're doing our remote learning, you're actually using these two devices, and you literally have one that's a generator and one that's a motor in a way. So any type of headphones, so if you are using headphones to hear this, the only way you're hearing this is you have basically the electricity that's coming out, whether it's through the music or through the recording of my voice, and that basically gets put through a transformer inside your headphones. And so you basically have electrical energy that goes into the headphones and it gets converted into pressure or sound waves. That sound wave is a mechanical wave. Okay, that's exactly what this is. You have a motor. So you have, again, electrical energy. Think of this from your battery if you're looking in a motor. And this would be your armature that would spin. Okay, that's kind of the parallel. But with your headphones, if you take them apart, you literally have this neat little converter. It's basically a subwoofer that is going to convert that electrical energy into the sound waves. And then I can pick this up then in my ear and I can sense it. Microphone works the other way. I basically take sound waves, which are pressure waves like this. Okay, so it's like me blowing on you. And again, a microphone through a transducer basically converts that into an electrical signal. And that electrical signal can then be picked up. So that is essentially a generator. So this is a neat little way of actually applying what we're learning. So again, one of the things we discussed in class is consider this sort of your exit slip. Make sure you can identify and verbalize the differences between a motor and a generator. And again, what are the energy conversions of each? Can you actually apply what we've learned to, again, this multiple choice question is what is a reason why a generator can produce electricity? That's a big thing. Okay, so again, what is this whole definition of electromagnetic induction? We completed this question as a class, but again, always a good review. That could you actually identify the motor versus your AC versus your DC generator? And the answers are posted a little bit further on. And then the last skill set is make sure you know your basic vocabulary. There's lots of vocabulary, so please make sure you can actually draw it out. Have a great way of summarizing this on your own. When you look at the slip versus split rings, make sure you have a way of actually remembering this. That's a really, really important part. I always remember that a split ring, I'm literally going to have a gap because it's split, so that might help you. And again, we talked about idea that if I have a slip ring, if I'm married, I have 2 rings, and again, I can slip them off and maybe have an alternate personality or an alternate sort of night around the town, so to speak. So have a way that you can remember this. And as promised, here are the answers, so feel free to pause this and make sure you can check your understanding.